Okay, and we're recording. Picking up with section 2.5 now. Now, real quick, per the announcement that I sent yesterday by email, this material that we're going to cover today is not fair game for the exam on Tuesday of next week. Right? That's just, the options are to have it fair game or have it not fair game. I think everybody wins if it's not fair game, right? But that does put us in this weird situation where we're covering stuff right before the exam that's not going to be on the exam. And I know that seems weird, right? So let me just remind you that, again, there is no reasonable alternative, right? And secondly, the exam that this will be fair game for, namely exam 2, it's only about 2 weeks away, right? So this is actually pretty relevant in the big scheme of things. Okay, so section 2.5, the chain rule. I'm going to segue into the multivariable chain. Oh, yeah, question.
Oh, I'm sorry.
It's all right.
Right above this, in the notes, there's like a note that's like skip Kepler stuff.
Yeah.
Is that in the exam?
No. The Kepler stuff is not on the exam. And by the way, this is noted on the content syllabus. Oh. So you remember there's the included material and excluded material columns, right? So Kepler stuff, and I think I was a little bit more precise about it, right? But there's an entire subsection at least in the book that's all about Kepler's study of planetary motion, and you don't have to do any of that, with the exception of this what they call proposition 1.4, and it's just kind of a sort of product rule for parametric curves. Yeah, all right. Okay, so I'm going to segue into the multivariable chain rule with the single variable chain rule. I know that y'all know the single variable chain rule. My goal here is not to teach you single variable calculus. My goal is to set up a certain point of view that will help with the segue, that'll help with the transition. So in other words, we look at the single variable chain rule just a certain way, the multivariable chain rule is going to look very, very similar. Right? So this is pedagogical in motivation. So specifically now, I want to make a particular interpretation of single variable derivatives. Right? So here's a single variable function. X is the input variable, Y is the output variable. If your input point were to move with some velocity that I'm going to call x prime, well, if you move the input, that's going to make the output move also. Let's suppose that the output's velocity is y prime. Seems like a reasonable thing to call it. The feature of the derivative that I want to talk about here, among the many interpretations of a single variable derivative, I want to take this point of view that it is the thing you multiply by input velocity to get output velocity. Okay. Everybody comfortable with that interpretation? Again, among many others. Okay. All right, so now let's apply that point of view here in this circumstance where I have a composition. So on the one hand, let's see, I have to make some color choices. There is this function here that turns x's into y's. And then we're going to have, let's see here, color choices. This function here that turns y's into z's, and well, if f turns x into y and g turns y into z, I can compose those functions. I can take the output from the first, make that the input to the second. Altogether then, I have a function that turns x's into z's. Right? And this composition function is what I want to talk about the derivative of. So, all right, now let's think in terms of inputs and outputs to these functions. If I were to have some, color choices again. If I were to have some point, let me use orange, some point over here, if it's moving with some velocity, then the output from f is going to be moving with some velocity. Well, of course, that's the input to G. That means that the output from G will be moving with, well, some velocity. Right? Now I want to talk now about these three velocities here. Right? There's the x velocity, y velocity, z velocity. Okay. So here's the innocent observation. Now you can write down a bunch of algebra like we've got there, and that's fine. And feel free to look at that if you like. Let me just skip to what I'm going to call the intuitively satisfying punchline. And that is, if I want to ask the question, what do I have to multiply by x prime to get z prime? In other words, what is this derivative? Keep in mind, the thing that you multiply by input velocity to get output velocity is the derivative, right? So if I want to know what that derivative is, what do I do to x prime to get z prime? Well, it's pretty easy to read right off of the diagram here. Apparently, I have to multiply first by f prime. That gives me y prime. And then after that, I then have to multiply by, I forgot what color I used, multiply by the derivative of g to turn that into z prime. It's a two-step process. Each one of these steps along the way, you multiply by a factor. And so if you multiply by a factor and then subsequently multiply by another factor, altogether you have multiplied by the product of those two factors. That's a pretty innocent observation if you think about it. Okay. All right. So now there's different ways to say this. I like the idea that differentiation turns a composition into a product. After all, we were looking at a composition of functions, and the result was that the derivative is a product of individual derivatives. Right? So I think this is a really nice way to think about it. It rolls off the tongue pretty nicely as well. That's good. Okay, now with that point of view on single variable calculus in mind, let's do the same thing now in a multivariable setting. So let me remind you again, we have a lot of different points of view on multivariable derivatives. Various different interpretations, geometric and algebraic and otherwise. But the one I want to take is that if you have a multivariable function, if you have an input velocity, so your input point is moving, right, with some known velocity. And that, of course, results in the output moving with, let's say, some velocity. We know what you have to do to the input velocity to get the output velocity. The answer is that the thing you do to the input velocity is you multiply by the derivative matrix. Right, now, just as a reminder, this is morally equivalent to what point of view that we took on single variable derivatives, right? The derivative is the thing you multiply by input velocity to get output velocity. Purple times green equals blue, if you like. Everybody good? So we're taking the analogous point of view. Let's now apply that analogous point of view again to a composition. So, okay, well, we've got some input velocity, some then you might say intermediate output velocity, which itself then causes velocity in the ultimate output. So said differently, if you know x prime, namely the velocity in the sort of the x space, that allows you to conclude the velocity in the y space, which allows you to compute the velocity in the z space. Now, altogether, let's see here. Can I fit? Yeah, I can. Close enough. Altogether, what would I have to do to x prime to get z prime? Altogether, what is the what do I have to do to input velocity to get the ultimate output velocity? Well, it's a sequence of steps, right? If you want to turn x prime into z prime, the diagram, right, is already kind of telling us the first thing I've got to do is whatever it is that turns x prime into y prime, that's multiplication by the df matrix. And then after having done that, what do I have to do to turn that into z prime? Well, you've got to multiply by the dg matrix. So altogether, the big purple arc of turning x prime into z prime is a two-step process. First you do the dark green, then you do the dark blue. Everybody on board? So, altogether, the thing that you multiply by x prime to give z prime is this product. This time it's a product of matrices instead of a product of scalars. But strategically, it's the same idea. Okay, which then gives us the same sort of rolling off the tongue summary of this process. You know, what this says right here is that let me highlight actually. I'll do it like this. Differentiation turns a composition into a product. Same results, same, little pithy summary here as in single variable. It's just that now they're matrices. Is everybody happy with that? Seem kind of believable? Does everybody see the analogy? Okay. All right. Now, there's a little subtlety here that I do need to talk about, and you'll probably recognize from the single variable version of this, but it's about where are these matrices evaluated. Let's see here. So where is this matrix here evaluated? DF evaluated where? Well, look, F is being evaluated at that point, right? It's whatever the values of x1 and x2 are, that the point is what we're calling A. So DF is evaluated at the point A. That makes sense? Same thing in single variable calculus, of course. Okay. What about the composition? The composition is also evaluated at the point A, and so the derivative of the composition also evaluated at the point A. No big deal, right? That's where that composition function is acting. So therefore, that's the point from which x prime is moving. That's the point where I need to know how to do stuff. All right, well then let's not forget what's the deal with G though. G is being evaluated at this point here. That is not A. Right? That point's not A. A is way over here. A has never heard of G. A does not go into the function G. G is being evaluated at this totally different point. Right, now, we can think about what that point is. That point is, let's see here. It would appear to be that this is the point that comes out of the function f when you plug in a to the function f. So that's f of a. Sure. It's not a. Okay, so there's a little subtlety you got to keep track of there, easily forgotten, but that needs to be evaluated at f of a, not a. Okay. Fine. Moving along, let's do, and then real quick, I in this example here, just for ease of drawing the picture, I made this two-dimensional to two-dimensional to two-dimensional. That's just for sort of convenience. Nothing about the argument that we made here is intrinsically two-dimensional. In fact, just for humor value, let me point out that I could, okay, now it's three-dimensional. The argument doesn't change, right? So the dimensions don't matter. This product of derivative matrices, turning composition into a product, is valid no matter what the dimensions are of the functions that you're looking at. Okay. All right. Okay, so example. Now here's a couple of functions. The function f takes x1 and x2 as its inputs, gives us y1, y2, y3 as outputs. This next function g takes those outputs, the things that came out of f, then are the things that go into g. So this is, of course, what happens when you compose functions. F is acting first. Whatever its outputs are, g acts second on those outputs. And then G produces Z1, Z2, and Z3. Okay. And what I want to do is, and there's a bunch of information given here. We'll figure out later how to actually use this information. What I want to do is I want to compute this derivative matrix. And then momentarily we'll come back and think about that partial derivative. We'll come back to that in a minute. But first let's talk about the derivative matrix. Okay. Well, the derivative matrix, we have a formula. Here's just straight up copying from the previous page. Right? That's just a multivariable chain rule. By the way, this is what we call the matrix form of the multivariable chain rule, because all of these are matrices. Turns out there's another form of the chain rule we'll talk about in a few minutes. But for the moment, anyway, we're just going to do the matrix. So, yeah, there it is, pure copy. How do I compute these matrices? I don't know either of these functions. F is not given. Right? G is not given. So, golly, I'm hoping I can actually evaluate these matrices. Now, freebie, df evaluated at the point 1, 2. Look at that. Given. Sweet. Right, it's exactly what we needed. I don't need to know f. I know the derivative matrix for f because it was given in the statement of the question. Okay, that's nice. Okay, but I'm also going to need to know dg at the point f of 1, 2. Okay, what is the deal with f of 1, 2? Well, here's another sort of given. F of 1, 2 is given to be 3, 1, 0. So I'm just going to plug that in. F of 1, 2 is 3, 1, 0. And now my question becomes, all right, now I need to know what dg is at the point 3, 1, 0. Oh yeah, okay, sweet. Another lucky break given. Everybody happy? Okay. All right. Okay. Yeah, boom. We recopy those, and we know how to multiply matrices. Make sure you know how to multiply matrices. And here's we're done. We've now computed that composition derivative as this matrix right here. Now, before we go on to the partial derivatives, everybody good with this part so far? Okay. All right. So now, how do we compute this partial derivative? What we have to do is think about what does it all mean? What do Z3 and X1 have to do with this question? And I make a couple of observations. First of all, notice X1 is the first input variable to F. That makes it the first input variable to the composition. First input variable. I want to know, it seems, a partial derivative with respect to the first input variable. And because it's with respect to the first input variable, it's going to be in the first column of the derivative matrix. Now, I remind you that the organization of the derivative matrix, right? Columns correspond to which input variable you're taking the partial with respect to. Rows correspond to which output you're taking the partial of. Okay, so input variable corresponds to column. Everybody happy? Okay. All right, now let's think about the next thing that we've been asked, the next aspect of what we've been asked about. We've been asked to compute a partial of Z3. What is Z3? Where's Z3 in this question? Here it is. It's the third output variable, apparently. Okay. Well, if it's the third output variable, that means I'm looking for the entry in the third row of my derivative matrix. So, this thing that we're looking for, being as it is a partial derivative from the composition, it's one of these entries up here. It's one of the elements of the derivative matrix, and based on the arguments we just made, well, it needs to be in the first column, and it needs to be in the third row, and so therefore the number that we're looking for is 3. What do you think? Everybody's good? Okay. Cool. All right, now real quick, I'm going to show you a couple of special cases. These are not deep observations. This is just kind of a, oh, hey, check it out kind of thing. So I'm going to go quickly through these examples. Pretty straightforward. What would happen? How does the chain rule cosmetically change if there's only one original input variable? Right now, we still have several of the middle variables, and then several of the outer variables. But if there's just the one input variable, all right. Well, my first function has only one input variable, and therefore there's only one column to the DF matrix. The DX matrix. Sorry, the first function. Is that right? Okay, likewise, the composition also is a function of apparently only one input variable, so its derivative matrix has only one column. Yeah? So altogether then, if I look at the function f, its derivative matrix goes here, and what I have then is a statement about think of this as a statement about what the df matrix does, and it turns this green vector into that purple vector. And if you think about it, this is what you might call, let's see here, you know what, I'm going to leave that arrow like this. This green vector right here is a velocity. I'll do it like this. I'm going to pencil. It's a velocity in Rn. It's dx dt. It's the velocity in what you might call the domain of f. And then let's ask the question, well, what is this thing here? Well, that's the velocity in the target to f. So the punchline is what the chain rule has turned into in this special case is it's a restatement. It's what I'm going to call old news. We already knew that apparently a derivative matrix is what you multiply by an input velocity to get an output velocity. Again, we already knew that. Right. So, anyway, it's nice, I think, to see though that the chain rule it has this known fact as one of its special cases. Or you might say the chain rule is kind of a generalization, maybe, in some sense, of this known fact. So, all right. So now here's an example. I'm not really sure why I'm doing an example here. I guess couldn't hurt, I suppose. But this is just an example of, again, what we already knew. We already knew that derivative matrices turn input velocities into output velocities. But here we go. Suppose you have some function here, f, right? 2 inputs, 3 outputs. And suppose that over here in the domain, we've got a particle that's momentarily at the point A, and it's moving with this given velocity 4-3. So we know the input velocity to this function f. The question is to compute the output velocity from f. And so this is just teed up perfectly for the result we have on the previous page. Input velocity times derivative matrix gives us output velocity. So all I have to do is compute this derivative matrix for this function, and you take some partial derivatives, you plug in the point in question, right? This is all being done at the point A, so we plug in A. Namely x equals 2 and y equals, x1 equals 2, x2 equals 1. To get those variables straight. And here's your derivative matrix. And then exactly as in some sense we already sort of knew would happen, this matrix is what you multiply by the input velocity 4-3 to get the output velocity df dt that we wanted. So there it is. A little bit of arithmetic in the final computation. How are we doing? Everybody see how that all kind of fits together?
Never mind.
Okay. All right, no worries. Okay, here's another special case. This is a special case of the special case. So we previously talked about what happens if there's just the one input variable and we end up with a relationship between velocities, known fact, special case, etc. Okay, now, furthermore now, what if there's only one output variable as well? Okay, well, let's not forget that that's the output from this function f. This is where the derivative matrix for f goes. If there's just the one output, that means that this derivative matrix has just the one row. And so, well, then this is what the chain rule turns into. Instead of having a, what you might call, a full size, thick derivative matrix that's multiplying by input velocity to get output velocity. Now it's just a single row matrix, filled matrix. And this is getting to a point of algebra we've already talked about, and that is if you multiply a matrix times a vector, but if that matrix has just a single row, that single row morally it's got all the same entries as the gradient vector, and that matrix vector product is computationally identical to this dot product, right? And so that's why, if you have just a single output, you can think of the derivative as being a matrix, or alternatively, you have the option to think of the derivative as being dot product with the gradient. And, again, suit yourself, it's morally identical, but it looks different on the page. But anyway, it's a sometimes convenient alternative point of view. Yeah.
Can you kind of re-explain, why for the kind of 1 by n matrix you have, you're using partial derivatives?
Oh, yeah.
But on the vector, it's...
Yes. Okay. So partial derivative is you have to write partial derivative if there's several input variables, but in actuality you're going to hold most of them constant, right? This whole business about holding most of them constant, you have to fess up to that. That's not something you can just ignore, right? Yes. So partial derivative has to be denoted when there's other variables that you're holding constant. So now here. With this matrix, there's several variables, evidenced by the fact that there are several columns, right? So if there are several variables, then for any one of those, I'm going to be holding the other variables constant, and so these have to be partial derivatives, right? So on the other hand, if you look at this matrix right here, that's the derivative matrix for this function, there's just the one column. That means there's just the one input variable. So, I guess you could say what we call vacuously, I'm holding the other variables constant, but actually there's no other variables. So I don't have to hold them constant because there aren't any of them. So said differently, I can just call them just regular old derivatives. Yeah. Is that cool? Yes. Everybody happy with that? Okay. All right. Okay. So again, example. Again, I don't really need to do this, but might as well, I suppose. So this is an example tailor-made for this situation. There's a single input variable and there is a single output variable. Specifically here, the single input variable is time. Position is a function of time. Bird's flying around. He has a position as a function of time, right? And then as a function of position, there is this one single output variable. I didn't even give it a name. Oh, I guess I did, didn't I? I'm calling that one output variable. I'm calling it T. Capital T for temperature. So temperature is a function of position. Position is a function of time. The composition then is a single variable derivative of scalar temperature with respect to scalar time. And using the formula on the previous page, dot product with the gradient does the trick for us. And so all we've got to do here is we've got to take this function here and compute its gradient. Okay, and there's a little bit of calculations that go into that, but that gradient turns into this vector right here. The velocity of the bird is given. That goes there. And again, a little bit of arithmetic, and the dot product gives us that our final answer is that. So just immediate plug and chug example of using this formula for this circumstance. Okay, so now I want to give y'all a different point of view on the chain rule. I emphasize this is has its moments. I like it for the special case moments where it is kind of useful, but I strongly advise you not to make this your primary point of view on the chain rule. I think it's ultimately more of a mess. It's nowhere near as simple. This, I believe, should be your primary point of view on the chain rule, and view kind of any other version of the chain rule as being, okay, well, I guess a special case if you look at it a certain way, you know, that kind of a thing. But this is the chain rule to me. Okay, so that said, let's see what it looks like when you kind of crank it out. So here again, we have a composition of functions. Here's what the chain rule says for this composition of functions. Now let's just for bookkeeping purposes kind of carefully write down that we've got the x variables, and there's a function of the x variables that gives us the y variables, and there's a function of the y variables that gives us the z variables. Okay, so specifically f is what turns the x's into y's, and g is what turns the y's into z's. Okay. All right. So then the composition then, this is g compose f, is what turns the x's into z's. So altogether, if you write down the chain rule, right, the matrix form of the chain rule for this arrangement of functions, that matrix form of the chain rule is like so. Okay. Now, that said, let's ask a related question. Hypothetically, I might care about this sort of thing. What if I were interested only in one specific entry in this composition derivative? I don't care about any of the other entries. I just want to know just that one only. Well, if I only want to know one entry in a matrix that's a product of two other matrices, we have a formula for this, right? I can take the corresponding row of the left matrix and multiply by the corresponding column, dot product that is, corresponding column of the right matrix. And so this single entry that I'm looking for here is that dot product, and you can see the, what you might call the green entries right there. And you can see the blue entries like so. And all together then, instead of having to write down this great big monstrosity of a chain rule, interested as we are only in that one entry, I can write down this only slightly monstrous scalar version. Anybody see that? Yeah, this comes up surprisingly often. Right, that you don't actually care about most of the outputs, just the one. Okay, so before I get into it, so there's another way to think about this formula that I think is really valuable. I'm going to spend some time on it in just a minute, but before I get to that, I want to dispel a dangerous misunderstanding. Very common misunderstanding. A lot of students, when they're starting to write this down, right, they say, okay, all right, well, this is the partial that I want, and it's equal to, okay, well, here's the first term, and then they think to themselves, oh, wait a minute, I guess I'm done because that and that cancel, and this is that, and this is that, and so sweet, we're done. Right? You can see the temptation. It is tempting. Okay, well, there's a couple of things wrong with that. First of all, that's not how matrix multiplication works. Right? It's clearly wrong. So, okay, well, yeah, but what's wrong with this reasoning? What's wrong with the idea that I can just cancel these things? And ultimately, the problem is misinterpreting the notation. And whose fault is this? Honestly, it's the notation's fault. The notation is really bad. I don't know a better alternative, but it's pretty bad in some important ways. So this thing here, let's just a little bit easier to look at it down here. This thing right here looks like a fraction. It's not a fraction. I know that's asking a lot for me to, because we wrote it as a fraction. You just have to remember, it's not a fraction. It's a limit of certain things defined in certain ways with certain assumptions being made. But it's not a fraction. This thing by itself is not a thing. Right? If you're going to have a fraction, the numerator has to be a meaningful object. This isn't. Right? And then likewise, this is not by itself as written a meaningful object. So just as a for example of what I'm talking about here, let's think about what goes into this. When we're computing this thing here, what can I say, for example, about the other y variables? And well, this is a partial derivative. When you compute a partial derivative, you have to hold all of the other variables constant, right? The variables here are the various different y variables. So I guess these other variables here, I guess I'll do this in gray per my convention. The other y variables, while you're taking that y partial, must be constant, right? Okay, yeah, that's true for that partial derivative, but now let's come over here and think about what's going on over here. Forget about all the green stuff on the left. If I want to take the partial of y1 with respect to xj, that means that I'm going to hold all of the other x variables constant, but xj will be changing. And now let's think through what happens if xj is changing. Well, that's going to make y1 change, but it's also going to make y2 change. It's going to make all the y variables are going to change. We're changing their inputs. So in this scenario over here on the right, the y variables are not constant. So what we have here is, you might say, sort of an incompatibility, right? Two different stories. So these things here, for which tragically we kind of seem to be using the same exact notation, yeah, they're not the same. They're part of different stories, right? Different hypotheticals and setups, and you cannot cancel them. I hope everybody's clear on that. Does that all kind of make sense? So beware of this. I keep seeing this happen on exams that students will be like, hey, look at that, it canceled, and boom, right? And it's dramatically wrong. It's super duper wrong. So please don't step on that landmine. Okay. All right. Okay, so moving along. All right, now here is a sort of a independent interpretation of this equation. Now again, this comes straight out of the matrix form of the chain rule, matrix multiplication and all that. But here's a different take, perfectly reasonable different take. What this says is I'm going to be moving xj around, be making changes to xj, and as I do that, I want to keep track of how zi is changing. Okay, so how am I gonna do that? Oh, and don't forget, this being a partial derivative, all these other x variables are constant. Okay, so the big idea is that when you change xj, a lot of things happen. For one thing, when you change xj, that's going to make y1 start to change. But it's also going to make y2 start to change, and blah, blah, blah. It's going to make all of these various different y variables change. And each one of those, for example, as y1 changes, that's going to make a contribution to how zi changes. Right? But then so is the fact that y2 is changing. That will make a contribution to how zi is changing, et cetera, et cetera. All right, so the way I like to think about this then is that the changes in xj propagate through to cause changes in zi along these various different paths. So as xj changes, that'll cause y1 to change, and as y1 changes, that will contribute to zi changing. So this path corresponds to a term in our formula. And specifically, notice that the factor, sort of the multiplicative factor there between xj and y1, there's that factor. It's that partial derivative. That's what that partial derivative is. It says when you change xj a little bit, how much does that cause y1 to change? And then this factor here, when you change y1, how much does that contribute to zi changing? That's right here. So you can think of each one of these terms as corresponding to a path. Everybody buy it? I mean, it's just a point of view. So let me clean up my picture a little bit. Each term corresponds to a path, and then furthermore, notice each path passes through exactly one of these, what we call intermediate variables. Because they're kind of in the middle, right? They're not the original inputs and they're not the final outputs, so they're the intermediate variables. So terms correspond to paths, which correspond to intermediate variables, and so you might say then terms correspond to intermediate variables. And then I can further sort of color code this. You can see the intermediate variable there and there. You can see the output variable there. You can see the input variable there. So I recognize this. Oh well, I'll do it like that. I recognize this as being the y1 term, you might call it, because it corresponds to the path of propagation that goes through the y1 intermediate variable. And then so likewise for all the other intermediate variables, there are paths which give rise to terms. Last one, for example, being this path for which ym is the intermediate variable, which you see the ym right there, and again, still zi there, still xj there, and so this very reasonably is what you might call the ym term in that formula. Everybody happy? All right. So the nice thing about it then, one of the things I really like about this point of view is arguably then you don't even really need to memorize this formula. You just need to understand the idea that changes propagate along paths and just understand what the paths are, right? And then you write down terms corresponding to those paths. The diagram memorizes the formula for you. That's very handy, very convenient. Okay, so let's see an example. Here we go. Suppose you're given these formulas. We're asked then to compute one of the partial derivatives. Note it's just a single partial derivative. They're not asking us about the derivative matrix here. We don't need to bring the big guns into this problem because it's just asking me about one particular partial derivative. Now, before we get into the formula and writing down the equation and stuff, I do have a strongly felt piece of advice for you when you see a question like this. Draw the diagram. It is unbelievably helpful. Let me say that differently. Without the diagram, it is extremely confusing. Wait a minute, which variable is where and what's a function of what and leads to what else? And oh my gosh, right? You can get so lost. The diagram is critical. Now, with that in mind, we're given that f takes x's as its inputs, gives y's as its outputs. So represented now on my diagram. Likewise, we are given that g takes the y's as the inputs and gives these z's as the outputs. Boom, on my diagram. So now I can see exactly what is a function of what. The diagram's going to do my bookkeeping for me. It's going to make all my decisions for me. As what terms do I need to have, blah, blah. Okay. So with that diagram drawn, now it's just, okay, well, I was asked to compute the partial of Z2. Okay, let's see here. There's Z2. And I want to compute that partial with respect to X2. There's my X2. Okay, go diagram. There's my first path. That gives me this as my first term. Notice y1 is the intermediate variable. This is therefore the y1 term. And then let's see here. Here's the second path. That gives me this second term where y2 is that intermediate variable. So I didn't have to sort of like even I mean, I had to see the diagram. I had to understand how propagation of paths works. Other than that, I just had to understand what these terms look like and just kind of copy them down almost from what the diagram tells me. Everybody good? And now it's all downhill from here. It's a couple of easy partial derivatives that you need to compute, and that's no sweat. What is the partial of Z2 with respect to Y1? All right, well, here's Z2. The partial of that with respect to Y1. Cool. Nothing to it. A little algebra. Yada, yada, yada. Everybody happy? Okay, big trick, diagram. Don't forget to draw your diagram. Okay. Now, a couple of quick warnings. Confusion of variables is a nasty problem. Nasty. Try not to put yourself into a circumstance where you're vulnerable to possibly accidentally stepping on a confusion of variables landmine. It's just don't even put yourself in that circumstance. Here's a single variable example. This is a Calc 1 problem. Yawn. I know y'all know Calc 1. No problem. But just as a segue, here's a couple of functions. Nothing wrong with these functions. Perfectly reasonable little functions. I am very much within reason to want to compose them. Once I've composed them, there's nothing insane about wanting to take a derivative. Right? Perfectly reasonable question. And here's a mistake that one could imagine Calc 1 students would make a lot, and that is to say, okay, well, let's see, a derivative of compositions, the product of the derivatives. And well, let's see here, G prime, okay, well, there's the derivative of that. And let's see here, F prime is, okay, well, there's the derivative of that. And then you multiply these and you get 6x cubed, which of course is wrong. Now I was deliberately sloppy there, right? A more careful, writing of the chain rule recognizes that G prime has to be evaluated not at x, like I did here, but at f of x. F of x, of course, being x squared. So you plug in the right thing into G prime, and then all of a sudden, of course, you get different algebra, which works out to a correct answer. But I'm going to complain about this calculation here as well. I didn't step on the landmine, but there was still a landmine that I had to step over. Right? That's scary. So here's what I propose is really just a much better solution as follows. Let's just recognize that while there's nothing really wrong with how these functions were given to me, as soon as I realized I was composing them, I kind of needed to rewrite these functions. So specifically, if f is x squared, if I am writing f as being a function of x, what name am I going to give to this output variable? What should I call the output from f? I better not call it x. That'd be ridiculous. X is the input, not the output. So I guess I better call this output y. Okay, but well, wait a minute then. If y is the name that I give to the output of the f function. And if I'm going to be plugging in that output as an input to g, I mean, I'd really better write g as being a function of y. This is pretty wrong right here. Once I know I'm composing these functions, this seems to be suggesting I'm doing g as a function of x. It really importantly isn't. G is a function of the output from f, which we just agreed to call y. So what you've got to do then is rewrite the second function. Now what I've got in blue here, highlighted in blue on the top and the bottom of the page, is the exact same function. G is not changing at all. G is still G. G is still the act of cubing whatever you put into it. I'm just writing it now with respect to a different, more appropriate dummy variable. Is that cool? All right. Okay. And then I guess I can call that output that comes out of G, I guess we can call that Z. Not that we really have to, but whatever. Okay. And now, having set it up this way, I don't have to step over any landmines anymore. There is no landmine. The landmine's gone. Because, look, I can play fast and loose again here. The derivative of composition is the product of the derivatives, and I just, happily, blindly compute the derivative of f as, I guess 2x. But just, boom, let's not worry about anything. And then what's the derivative of g? Okay, boom. I'm not thinking about what I'm plugging into it. If g of y is y cubed, then the derivative is 3y squared. Whatever. And having done that, notice the notation itself forces me to plug in the right thing for what I have called y here, because after all, y is x squared. And doing that gives me, whoops, I wanted that in a different color, gives me the right answer. Everybody good? So that's all single variable calculus. I know you know that. You may or may not have seen this, confusion of variables concern, rewriting the function, whatever. But anyway, it's easier to understand in a single variable context. The multivariable takeaway is just do the same thing. So here's a couple of functions. Nothing wrong with those as functions. Perfectly reasonable to compose them. Perfectly reasonable to want to take a derivative. Fine. Well, let's be careful, though. Let's not confuse our variables. Here's our diagram. If f is going to be a function of x and y, if x and y are the inputs, then these outputs from f, I can't call them x and y. I'd better call them something else. I don't know. Let's call them u and v. Whatever. Well, once I've called them u and v, that means I kind of have to then rewrite g as a function of u and v. And so I have to take this otherwise perfectly reasonable way to represent the g function. I need to rewrite it in terms of u and v. Same exact function, didn't change the function, I'm just changing the dummy variables. Having done that, again, you can, stroll comfortably through the little field that is this question. There is no landmine. So we take the derivative matrices, we multiply the derivative matrices per the chain rule. Yawn, just write them down, multiply them, nothing to worry about, nothing bad to happen. And then when you get to the point, and wherever it is, whether it's after you multiply or before you multiply, it doesn't matter. There's this reminder right here that u is x squared plus y squared. So everywhere you see a u, to plug in x squared plus y squared. Likewise, everywhere you see a v, that's x squared minus y squared. And then, multiply anyway, we don't have to multiply it out. Everybody good? All right, Here's a related issue. Watch out for meaningless nonsense. It's a real serious problem. Very importantly, when you're going to do the chain rule, don't forget what the chain rule is. The chain rule is about compositions of functions. This is important. It's compositions of functions. Functions are pretty well-defined things, right? They have input variables, they have output variables that are not the same things. Right? And composition is a pretty well-defined thing. What comes out of the first function has to be what goes in to the second function. They got to be the exact same things. So if you find yourself in a situation where, let's suppose you're given a bunch of equations where this would appear, at least at a glance, to, when you're looking at the equations you're given. If this is what your diagram looks like, you got a problem. In what way is this a composition of functions? What is Z1 a function of here? Right? Is it a function of these variables? But they aren't even independent. Right? This is an awkward problem because Y1 is a function of, among other things, X1. So, X1 and Y1, these variables here are not independent. This is a problem. Right? The chain rule, as we have it written previously, does not address this. Okay. All right. Okay, so what you got to do is just fix the diagram. It's actually not that bad to do. Let's suppose that this is our question here, and what I've done is I've started with a collection of equations that actually produces this exact, what I'll call diagram here, right? What's a function of what? In these equations is the same as the way that diagram's laid out. And let's suppose you're asked to compute a certain partial derivative and you're going to want to apply the chain rule, right? You've got to fix your diagram. This is not a diagram that our chain rule, as we understand it, applies to. So here's how I'm going to fix it. I'm basically going to stick in another variable right there. The way that's going to fix our situation is I'm going to then view Z1 as being just a function of those variables. No problem. Z2 is a function of those variables. Those being functions, as indicated here. This, for example, is going to be a function of those. Now, wait a second. I need for Z1 to be a function of X1. Now I've got Z1 as a function of that thing, whatever that is. Isn't that cheating? Not really, as long as I make sure that whatever that is actually equal to X1. Right? So that's the fix. It's not even a hard fix. Just introduce a new variable in a place that makes your diagram fixed and just make sure it's equal to, well, whatever it needs to equal to. I need that to equal to that. Cool. So I introduce that one new equation. Now my diagram's good. Perfectly good diagram. Right? The Z's are functions of those three variables. Those three variables are functions of these. Write down the chain rule. Okay, so specifically, if you want to know what is the partial of Z1 with respect to X1, so I want to know let me do with the color coding again. I want to know the partial of that with respect to that. All right. Cool. First path, first term. Second path, second term. Let's see here. Third path, third term. Nothing to it. Boom. And then there is one extra little convenience I can notice, though, and that is this factor right here, the partial of x1 star with respect to x1. So this little red segment right there, what is the partial of x1 star with respect to x1? Okay, well, that's the world's easiest partial derivative question. x1 star is x1, right, by deliberate arrangement. So that partial derivative is 1, and so that factor just kind of disappears from that term, and we're all good. So anyway, just heads up, always make sure that your diagram actually makes sense before you start writing stuff down. Then you'll eventually either find yourself going around in sort of algebraic circles or at a dead end of some sort. Something will not fit and won't make sense. How would you feel about all of this? Okay. By the way, for whatever it's worth, I think this is a very underappreciated topic. This kind of situation comes up an awful lot in practice, and it seems to be pretty studiously avoided in a lot of textbooks. So I kind of had to, I'm going to say, figure this out for myself. My professors would say, oh, well, in this case, and they, in some sense, they have this picture in their head, but they didn't write it down for me or tell me about it. All right. So I always found this very, very confusing. But if you just do this as needed, everything works out very, very directly and simply. Okay. All right. Okay. Second derivatives. Quick pause. Y'all recall, of course, that the content of this course is listed in the content syllabus, right? It's a bunch of sections from the book. And then there's a listing at the top of the prerequisite material and all that. And then there's some extra columns on the right-hand side. One is called excluded material. That lists stuff that you can safely ignore, you're not responsible for, right? But then there's also a column called included material. And that's stuff that's not in the book, but is part of the course. It is fair game for the exams. You are responsible for it. It's stuff that I'm going to be doing in class that's not represented in the book, right? And so this is the first example that we're seeing here in the course of one of those topics. So the second derivatives with the chain rule is not mentioned that I've seen in our textbook. I think that's tragic. It's a pretty important topic. My experience as second major in physics, I used this a lot. And it's very confusing until you make certain insights. So I consider this to be one of the most important things in the entire topic of the chain rule, and thus that's why I'm adding it into the course. A lot of y'all are engineers. Again, engineering is not that different from physics. You're going to encounter stuff like this, and so it's very important that you know how to deal with this scenario. Okay, so here we go. Mostly, I'm just going to show you how this works by way of example. But roughly speaking, the big point is that if you have a function of x and y, just don't forget that its partials are also. Right? And the easy example, if you just take any function of x and y, pretty much, take its y partial, still a function of x and y. So that turns out to be pretty much the point. All right, so here we go. Here's my scenario. Suppose you have z as being a function of x and y. Don't forget what r and theta are, by which I mean don't forget that x and y are functions of r and theta. And I remind you that's the point of view I like to take on polar coordinates. X and y are functions of r and theta. Now, also, reminder, as stuff is given to you in the statement of the question, be generating your diagram. Really, really helpful. As in, I don't know how to do these questions reliably without having a diagram either written or, I guess I could keep the diagram in my head, I suppose, but why would I want to do that? That seems, unless it's really, really obvious, really, really easy. When you're learning this material for the first time, you should absolutely always generate your diagram on paper. It's tremendously helpful. Okay. Everybody good so far? Now, here's unremarkable observation. If you want to compute the partial derivative of z with respect to r, well, we've got x path and thus an x term. We've got a y path and thus a y term. Right? That's just a chain rule. I didn't do anything weird there. Of course, partial of x with respect to r. I know what x is. X is, it's the polar coordinate formula. It's r cosine theta. So the partial of that with respect to r is just a partial derivative calculation, nothing to it. And likewise, partial of y with respect to r, a straight up partial derivative, nothing to it. Okay, everybody's happy? Haven't really done anything substantial yet. Oh, and then there's this notational thing. Recall that there are these cases where, this is going to be our first real serious example of this. Sometimes, I have observed previously, this notation's a little too clunky, and it's kind of nice to write it with this more compact notation here, z sub x. All right, I think that's handy. Certainly in this case, it's going to be very convenient. And then likewise, zy down here. Okay, so is everybody happy down to that? All right, now let's look at the question that was actually asked. The question was to compute the second partial of z with respect to r. Right, yes?
Something I'm confused about is it looks from the diagram, you're taking r, and you're splitting it into its components of x and y.
That's not the intention of the diagram. The intention of the diagram is just to recognize that x is a function of r and theta, and that y is a function of r and theta. But once I realize that I'm only interested in how to get from r to z, these are the only of those arrows that I actually kind of care about. I don't really care about what may have been a function of theta, because theta is a constant now, because I'm taking a partial derivative with respect to r. Does that make sense?
Yeah.
Yeah. So, I totally get that, if you just, kind of looking at the way this is written, it kind of looks like what you described, that I'm breaking it apart or something, but that's not at all the intention. Is that satisfying? Okay. Good. Anybody else? Okay. All right. So, we have computed the first partial with respect to r. We want the second partial with respect to r. So we need now to take the r partial of this thing. The r partial of the r partial. All right. Okay. Well, so as I've written here, let's see here. I think this is our ZR. And so we're interested in taking the r partial of that ZR to get the second partial that we're actually interested in. Again, don't forget, we've already computed that first r partial. It was this formula here. Okay, so we're good down to here. Now I want to look at this equation here and ask what to do about this. What, for example, will I do when I get to the point where I'm taking the partial of zx with respect to r? Zx is not on my diagram up there. Is Zx a constant or something, or how do I deal with that? Right? Now, let me show you what some students do. The following is a catastrophic faceplant, unacceptable nonsense garbage. But I see it a lot, and so make sure you don't do this. This is really, 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 really wrong. Students will say, okay, well, I had Zx. That means I was taking the partial of z with respect to x. Now I want to take another partial with respect to r. How about I'll just say zxr? It kind of seems reasonable from the point of view of just notational, the superficial, cosmetically it kind of seems reasonable. But the thing is, this notation here where you list subscripts, right? These variables that you're taking partials with respect to have to be part of the inputs to the same function. So this would suggest that z is a function of a list of independent variables that includes both x and r. How in the world is that supposed to work? If z is a function of, both x and r, it's like I would have to include all of these. It's like now z is a function of 4 variables, but it can't be. These variables aren't independent. This doesn't make any sense. That's not a thing. Right? It's just garbage. It's not meaningful. So you can't do that. Not a meaningful thing. Here's what you can do, though, and this is the reasonable way to address this. You've already seen it. Obviously, I've revealed this new diagram here already, so you've probably seen this already. But as we previously noted, I'll come back up here for a moment. If z is a function of x and y, then so are its partials. The partials of z with respect to x and y are functions of x and y. So zx is a function of x and y, and zy is a function of x and y. So we update our diagram. Arguably, as soon as we get to here, we kind of ought to update our diagram to just represent what zx and zy are, where they fit in, what they are functions of, and therefore how to consider their derivatives. And specifically then, pretty quickly, we're going to find ourselves, let me not get ahead of myself. Let me talk about this derivative right here, partial of zx cosine theta with respect to r. We're taking a partial with respect to r. That means r is our variable. That means theta is a constant. That means cosine theta is a constant. That means that constant factors out. Right? Neat observation. Very important. By the way, thank you. Diagram. It's really helpful to see on the diagram that you can just casually inspect and be like, oh, I'm taking a partial with respect to r, so boom. That tells me what I get to treat as a constant. Gotta love it. So, okay, so theta is a constant, and then likewise this sine theta factors out. And as predicted, we find ourselves looking at a partial of zx with respect to r. And with our diagram appended as it is, there's really nothing to it. There's zx, there's r. I've got a chain rule problem. I've got what you might call a second chain rule problem. And I can even see what the paths are. There's what you might call the x path. Right? You can see the x intermediate variable there. And then there's the y path. You can see the y intermediate variable there. And so that's how the chain rule allows me to rewrite that expression, partial of zx with respect to r. Everybody good? The key concepts here, for one thing, diagram. For another thing, always keep track of, wait a minute, what's a variable, what's a function, what's a constant, which you will keep track of by way of the diagram, right? And then also just, real quick, don't try to move too fast. A lot of students will make mistakes because they try to go, from here all the way down to here, maybe all in one step. And so it's really easy to, and I missed from this all the way down to all of this. There's a lot going on there, and don't try to do too much in your head. So, one little micro step at a time, factoring out the constants, this is worth a rewrite. And then you have a very simple, explicit chain rule problem to deal with on its own. And then, of course, in this other step over here, in this, now we want the partial of zy with respect to r, another little chain rule problem there. Everybody good? And the rest is just kind of computing, nothing to it. Partial of x with respect to r, again, partial of y with respect to r. These are all things that we can just compute directly from polar coordinate formulas. And then there's notational sort of rewrites. That's just zxx. And this is zxy, etc. And, you know, move terms around, common factors and all that. Okay. All right, and I think I'm out of time. Yeah, I'm out of time. Okay, so we'll draw the line right here. I do have, by the way, a really cool example to start next class with. This is really, I hope this is going to be really persuasive to why do you need to know the second derivative chain rule, because it's a powerful example. Yes?
In your very last bit, you should assume that zxy is equal to zy.
Yes, and yes, good catch. I should have said here that this function is twice continuously differentiable. I need to add that in. Yep, absolutely. Okay, see y'all later. Have a good one. Have a good weekend. Have a good extended weekend. See you on Tuesday for the exam, of course.